Well, let's get started. A couple quick announcements. So I'm gonna record the next lecture, and then we're gonna use Friday as a practice problem day. It'll be focused on methods for determining stability boundaries of forced oscillations. So related to what we'll go over in class today. I already posted homework 5. That's only going to have 4 problems on it. So hopefully you can use the additional time for yourself, but also maybe to start getting started on your project. If you have a background paper, read the background paper. Start figuring out which calculations you're going to work through for the project. But the next homework should be shorter than the previous for sure. And then on Friday we'll have a practice problem day, and then I'll remind you about when I post that lecture. On Monday, Ian Grooms is going to be a guest lecturer. He's going to talk about resonance. In particular, he'll talk about some applications to PDEs. And then the next bit of material actually is going to be sort of multiple scale methods for PDEs, both linear and nonlinear waves. The lecture for a week from Friday, I'm going to record because, well, there's a wellness day on Thursday, and then there's not really one on Friday, but it's sort of supposed to be like a spring pause. So we won't have like a synchronous lecture on Friday. So if you want to get Friday's lecture out of the way on next Wednesday, then you can go ahead and do that. And then we'll kind of be back to the regular schedule after that. Okay, so that's what's coming up. I'll send emails as I post materials. So we'll go ahead and get started today and start talking about, in particular, stability properties of what's called the Mathieu equation. Okay. In particular, we're going to kind of briefly.
We're getting a rectangle thing.
Oh gosh. Okay. It doesn't tell me that that's what's happening, but okay. How about now? Okay. All right. The weird rectangle. Okay. So we're going to talk about the Mathieu equation. And what this introduces for us is a non-autonomous feature of an otherwise fairly pedestrian linear differential equation. But what's interesting here is that we have some periodic forcing term, but it doesn't enter as an inhomogeneity. It enters in as a time-dependent coefficient of just the 0th order term y of our solution variable. Okay, we have periodic coefficients. Okay, so we can exploit that, right? It's not as if this is just some general function. So we might expect that we're going to have something like periodic solutions. Okay, but the issue could be that there may be unstable solutions, right? And so it's hard to maybe wrap your head around the intuition of what's going to happen here, right? Because it's not as if I'm forcing it, with some non-autonomous function that I know is at the resonant frequency. Okay, but this time-dependent coefficient may generate energy that does not dissipate in our system, and it will in certain regions of parameter space. And what we want to find is what are the boundaries between where we get stable versus unstable solutions, where this energy builds up and where it can dissipate. And in order to do that, we're going to take a slight detour into Floquet theory, which is basically the theory of linear differential equations when we have linear periodic coefficients. Okay. And what we're going to do is find the boundary between stability and instability for, in particular, the A epsilon plane here. Okay. So as this is asymptotics and perturbation theory, you might expect we've got to have some sort of small parameter to deal with. Okay, so what's Floquet theory? It just allows us to say something about linear differential equations that have periodic functions as coefficients. Okay, so real brief, elementary Floquet theory. So let's even take a very specific case where we have 2 pi periodic coefficients. Okay, what types of solutions might you expect there to be to equations like this? If I have 2 pi periodic in time coefficients, my solutions might be,
2 pi periodic.
yeah, right. So okay, just like if I have 2 pi periodic forcing, I might expect to have 2 pi periodic coefficients. Same thing if I might have 2 pi periodic solutions. Same thing here, I might have 2 pi periodic solutions if my coefficients are 2 pi periodic, okay? So let's assume, for instance, okay, that I have some solutions to an equation that has 2 pi periodic coefficients. I'm not saying what that is yet, okay? And it's of the form y equals a y1 plus b y2, okay? So let's say it's some second order linear equation, okay? And y1 of t plus 2 pi is then going to be equal to y1 of t plus some scaling beta of y2 of t, and y2 of t plus 2 pi is going to be, alpha times y1, and y2 of t plus 2 pi is going to be equal to gamma y1 of t plus delta of y2 of t. Why is that true? Well, because I know it's 2 pi periodic, so these have to be solutions too. And I know that in general, any solution needs to be of this form, okay? Because I have a linear differential equation. And so I can formulate my solutions always as the sum of these independent solutions, y1 and y2, okay? So these are also solutions due to periodicity, okay? So then in general, I can write my my solution y of t plus 2 pi is equal to a alpha plus b gamma y1 of t plus a beta plus b delta y2 of t. And I'm just going to call these coefficients a prime, although it's not a derivative. I'm just using the prime as an indicator. B prime y2 of t. So what? Well, that means that a prime b prime is equal to alpha gamma beta delta a b, okay? And in this case, if we choose A, B to be an eigenvector of my matrix M here, so we'll just call this matrix M, then this would imply that A prime is equal to lambda A and B prime is equal to lambda B. Okay. Well, so what? That means when we go through some period of the oscillation, the coefficients of my solution, okay, are going to be updated according to this this eigenvalue lambda. Okay. So that means that y of t plus 2 pi is equal to lambda y of t. Okay. Therefore, if I take mu to be equal to log of lambda over 2 pi, so lambda is equal to e to the 2 pi over mu, okay, then y of t is equal to e to the mu t phi of t, where phi of t plus 2 pi is equal to phi of t. Okay, so that means that y is going to be unstable if the real part of mu is greater than 0, and it's going to be stable if the real part of mu is less than or equal to 0. Okay, so by recognizing that each time I go through a period, okay, that's going to somehow update the amplitudes corresponding to my periodic function. Okay, I've recognized that there's some eigenvalues associated with the growth or decrease in that amplitude. And that's what this Floquet theory does for me. It's a stability analysis, essentially, for periodic solutions in this case. Now you can extend this to the case of nonlinear equations, and you can essentially linearize around nonlinear equations and perform the same Floquet theory analysis. That's a discussion for another time, but that's a whole, another aspect of dynamical systems that we could cover. Okay, so we want to apply this to our Mathieu equation in order to just basically look for the stability boundaries. And essentially, Mathieu equation, okay? And if we remind ourselves of that equation, okay, first of all, one thing we can note is that it's even under the mapping from taking t to minus t, right? Because d2 y of minus t dt squared plus a plus 2 epsilon cosine minus t y of minus t, that's still equal to 0. Okay, so I can reverse the order of time, and essentially I'll still have the same equation. Okay, so that means that if I have solutions of the form e to the mu t phi of t, this solution implies that e to the minus mu t phi of minus t is also a solution, okay? Because I should be able to reverse the order of time and still get solutions. So that means that the only way I can have solutions that don't grow are going to be if the real part of mu is 0, okay? Because I'm either going to have that this solution is going to grow over time or this solution is going to grow over time, okay? So for stability, we need that the real part of mu is equal to 0, okay? And we can find these regions in the A epsilon plane where solutions are stable. And we'll call these our stability regions, okay? And if you want to see these sketched out in total, it's in the last section of Bender and Herzog, which is referenced in the calendar. Okay. So we're going to use perturbation theory in order to find these. And we're going to start by assuming that A is greater than 0 and A is not equal to n squared over 4 for n is some integer. And we're going to show that y is stable for small epsilon, okay? And we're going to take regular perturbation expansion. Y is approximated by y0 epsilon y1 plus epsilon squared y2, so on and so on, okay? Now, if we plug that in, let's just look back at Mathieu's equation here, right? We just have our typical sort of second order operator, and then we have this term here. So we see that to first order, we're just going to have this term, this, and then, you know, y0 here, okay? So maybe just as a reference, we can rewrite that, right? So d2y dt squared. If we apply our perturbation expansion, right, we have y0 plus epsilon y1 plus a plus 2 epsilon cosine t times y0 plus epsilon y1 is equal to 0, okay? So at order 1, we're going to have y0 prime prime plus a y0 equals 0. This is easy to solve. We get y0 is equal to a0 e to the I square root of a t plus its complex conjugate, right? A0 bar e to the minus I square root of a t, okay? Now, just like the problems you've worked before, you can imagine what we're after at higher order. We want conditions in order to exclude resonant terms, or we want some condition in order to avoid unstable solutions, okay? So in this case, we're going to have minus 2y0 cosine t. It's helpful to convert this to complex exponentials, and then if we multiply out, we get minus a0 e to the I square root of a plus 1t minus a0 e to the I square root of a minus 1t. And then I'm just going to say plus the complex conjugate of those pieces there, okay? Now, what do we see here in terms of secular terms is that secular terms appear if the square root of a plus or minus 1 is equal to the square root of a, okay? And this is only going to occur if a is equal to a fourth, okay? But remember up here, I said to exclude these, okay? So that's the reason to exclude them, is to avoid secular terms, okay? So we're going to assume that doesn't happen. And as a result, okay, we can get that y1 is, well, let me just say in text that we excluded these, right? But we assumed a is not equal to n squared over 4. Okay. All right. So then what we get is that y1 is equal to a1 e to the I square root of at e to the it plus complex conjugates and a1 e to the I square root of a e to t e to the minus it plus the complex conjugates there. Okay. And yeah, and we can exclude the homogeneous terms. Okay. Now, if we go to next order, epsilon squared, we get that y2 prime prime, a y2 is equal to minus e to the it plus e to the minus it times y1. Okay. And again, right, we don't have any secular terms. Because a is not equal to n squared over 4. Otherwise, we would have, yeah, the possibility of a equals 1 in this case, and that could lead to secular terms. Okay. So we end up with y2 is equal to a2 e to the I square root of at e to the 2 it. And we also have a2 e to the I square root of at e to the minus 2 it plus complex conjugates. Okay. So overall, we end up with a series expansion e to the I square root of at, sum from n equals 0 up to infinity, epsilon to the n, a n, e to the int multiplied by that plus complex conjugates here. Okay. And then this plus complex conjugates. Okay. So the series converges for epsilon small enough. Okay. Therefore, y is going to be stable in this case. Okay. Now, these are just sort of general solutions. What we want to study is the boundary between stability and instability. And in particular, we're going to look near a specific value of a. A equals 1/4. So if a equals a fourth plus a1 epsilon plus a2 epsilon squared, and so on, we have some perturbation expansion in A. We want to ask the question, what values of A as a function of epsilon are going to lead to stable versus unstable solutions. Okay, this is essentially going to sketch out for us in A epsilon space the regions where we have stable and unstable solutions. Okay, now this approach here works for, you know, small enough epsilon, and then also excluding certain terms in A. But if we want to draw these stability boundaries that are going to be relevant to higher order and longer time scales, okay, and for epsilon away from the boundary, then we need to look at these long time scale behaviors. Okay, so to properly deal with our secular terms, we need to use multiple scales. Okay, so in particular, y is now going to be expanded according to this regular perturbation expansion, but each function, okay, is going to have two time scales, t and tau, which is epsilon t. Okay, and this is going to allow us to see how these amplitudes are going to evolve once t gets large enough. Okay, so just like previous problems that we've done in this type. So now at order 1, dt squared plus a fourth of y0 is equal to 0. And just like a lot of the problems that you, or several of the problems that you worked on the homework, right? We get some slowly varying coefficient of a periodic function plus its complex conjugate there. We could do this in terms of trig functions as well, but it works well for complex exponentials. Now, what happens at order epsilon is that if we look at the inhomogeneous parts now, okay, we have a1 plus 2 cosine t y0 minus now this second derivative with one derivative in the fast variable and the other in the slow variable acting on y0. So what does this set up for us? It sets up a differential equation that's going to describe the amplitude of y0. A1 now, a big A of tau plus I a prime of tau plus a bar of tau, all are going to multiply e to the I t over 2. And that's going to be a secular term because it's going to apply a resonant forcing to y1. Okay, so even though we have these periodic coefficients, right, they can serve to, you know, provide forcing as we climb the hierarchy of epsilon powers. Now, there's another term here, a of tau e to the 3I t over 2. It doesn't really contribute to the resonant forcing, but we may need to include it in our solution y1 if we're going to go to higher orders. Okay, we won't for this first go. Okay, but remember that, you know, you had to do that in some of the problems that you've looked at. Okay, now if I want to exclude secular terms, right, I just look at the coefficients to my secular terms and I set them to 0. This is going to generate for me a differential equation. Okay, I a prime of tau equals minus a1 a of tau minus a bar of tau. Okay, and then the complex conjugate I have is minus a bar of tau is equal to minus a1 a bar of tau minus A of tau. Okay. So there's a number of ways I could decompose. I'm going to decompose as A equals B plus IC. Okay. So in that case, I get, if I plug that into either of them, I get B prime of tau is equal to minus A1 plus 1 C of tau, and C of tau is equal to A1 plus 1 B of tau. Okay, taking real and imaginary parts. Sorry, this should be a C prime here. Okay, so just to make it clear. So taking real and imaginary parts, right? We're going to get this second order equation. Okay, this is often what happens. You have some differential equation for your complex amplitude. You have to figure out some kind of decomposition. You could do polar, you could do a Cartesian. We're going to do a Cartesian decomposition. Okay, this is going to generate a pair of equations now that are going to have solutions that'll give us this the evolution of this complex amplitude function. Okay, so then B prime prime of tau is equal to what? Well, I can just I can combine these two equations, and I get 1 minus A1 squared B of tau. Not hard to solve then. I get B of tau is equal to some coefficient big K, let's call it exponential of plus or minus the square root of 1 minus A1 squared tau. Okay. So now I've learned that my amplitude is going to be some exponential of the slowly varying time scale tau, and it's going to involve some essentially some eigenvalue. Okay, this would be like my Floquet multiplier here. Okay, now I can choose A1 so that the real part of this is going to be 0, right? Remember, that's what I want. Okay, so in order to avoid an instability, I need to make sure that the square root of 1 minus A1 squared is not real. Okay, so if A1 has magnitude less than 1, I'm going to have exponentially growing amplitudes. Okay, so if I want stable solutions, I just need to take A1 to have magnitude greater than 1. Okay, so what does this do for me? It starts to sketch out this polynomial that's going to describe the boundary between the stable and unstable regions in the A epsilon plane. Okay, so that means that near epsilon equals 0, okay, the stability boundary, okay, is going to be A is equal to 1/4 plus or minus epsilon plus some order epsilon squared terms, and I'll rewrite this on the next page and sort of draw it out. Okay, so if we look at the stability boundary, what's happening in the A epsilon plane is that A equals 1/4 plus or minus epsilon plus order epsilon squared terms. So if I now sketch out my domain here, okay, I can draw A here, and let's do this. Yeah, no, let's do this the other way around. Makes more sense. A here and epsilon here. I take A is equal to 1/4 here, okay? And then as I increase epsilon, right, then I'm going to draw out a stability boundary here. And in this direction, the stability boundary is going to go that way. Okay. So that means that as long as A is on this side, right, I'm going to have stable solutions, and I'm going to have unstable solutions over here. Now, I've only done this out to linear order. If I want to see more of the shape of this, I have to go to next order. And you can go many orders higher if you want, okay? In the homework, you're going to go up to order epsilon cubed for the first problem. We'll go ahead and do order epsilon squared now, just to sort of finish off this problem, okay? But before I move on, I'll just pause. Are there any questions about this approach? Okay, so this shouldn't be too far afield of kind of the amplitude equation approaches that we've had before. It's just that at the end of the day, the condition that you get is going to be relevant to the particular amplitude solution that you've solved for. And in particular, this coefficient up here, which is going to indicate your Floquet multiplier, okay? According to the elementary Floquet theory that we worked out before. Okay, let's go up one more order, okay? And we'll start by setting A1 equal to 1 plus A2 epsilon, and pursue some correction. Now, of course, one tricky thing about method of multiple scales always is deciding the scaling of your long time scale, okay? So you either sort of get that as you found by trial and error, okay? Or you can maybe find some other ways to figure it out. In this case, if I just plug this in, right, to my amplitude formula up here, then what I find is that B of tau is given by K exp of plus or minus the square root of minus 2A2 epsilon, okay? If I just only expand to first order in epsilon for that polynomial times tau. Now, if I pull this epsilon through now, I get K exp plus or minus the square root of minus 2A2 epsilon to the 3/2 t, okay? So what that should tell me is if I'm going to go search for the stability boundary at A2, that's going to be relevant at this sort of fractional time scale, epsilon to the 3/2 t. So that's where I need to be looking in order to find out something about A2. So we're going to use sigma equals epsilon to the 3/2 t as our time scale. And go back, okay? So what do we have so far on our stability boundary? Let's just pick one of them. Let's take the positive one, right? Let's take the plus epsilon one. And I still don't know what A2 needs to be. So I have plus A2 epsilon squared. And then here's my long time scale, epsilon to the 3/2 t, okay? And finally, okay, since I have a 3/2 time scale, probably that's going to generate terms on the half powers. So how do I manage that in my perturbation expansion of y? Okay, Well, just to be safe, let's take half powers of epsilon, okay? And it turns out what we'll see is that we actually have to go up to order involving y4 in this case, okay? So it just involves a lot of bookkeeping to climb the hierarchy of epsilon powers, okay? So epsilon to the 1/2 handles half powers, okay, from the time scale sigma equals epsilon to the 3/2 t. Okay. All right. So we're not going to finish this today. I'll probably stop kind of halfway through. So if I differentiate y then, okay, using these multiple timescales, I'm going to get dt squared y0 plus epsilon to the 1/2 dt squared y1 plus epsilon dt squared y2. And then it starts to get interesting at epsilon to the 3/2 dt squared y3 plus 2 dt d sigma y0, okay, plus so on and so on, okay. Now, we have to equate powers of epsilon to the 1/2. Okay. And at order 1, we get our just friendly old homogeneous equation that we know that we can solve. So we get y0 is equal to a0 of sigma e to the it over 2 plus some complex conjugate term. At order epsilon to the 1/2, we get dt squared plus 1/4 y1 is equal to 0. So again, we get y1 is equal to a1 sigma e to the it over 2 plus complex conjugates, okay? Order epsilon now is where stuff starts to leak in because of the periodic coefficient. And what we find is that our standard linear operator acting on y2 is equal to 1 plus, I'll just write it out, e to the it plus e to the minus it y0, okay? And I can work out all these exponentials. I get minus a0 it over 2 minus a0 e to the 3i t over 2 minus a0 bar e to the it over 2 plus complex conjugates, okay? Now we can take a0 equal to minus a0 bar to remove secularity, right? That's our amplitude equation that we get. The only e to the it over 2 terms here I have are just these two here, right? So that means that a0 of sigma is just going to be equal to I times b0 of sigma. Actually, let's just call this b because I don't think I'm going to have another b floating around. Okay, and this function here is real. Okay, now that means that y2 is equal to a2 of sigma e to the it over 2, just the homogeneous part, plus a half a0 sigma e to the 3it over 2. And we know what that a0 sigma is now, or at least the form of it, okay? Order epsilon to the 3/2, okay? I'm going to get these differential equations arising in the amplitude because I have this minus 2 dt d sigma y0 minus 1 plus 2 cosine t y1. And I can write this all out as minus I a0 prime sigma e to the I t over 2 minus a1 e to the I t over 2 minus a1 bar e to the I t over 2 minus a1 e to the 3it over 2 plus complex conjugate parts. Okay. Now, if we eliminate secularity, I a0 prime of sigma, well, I know that that's going to be equal to minus b prime of sigma needs to equal minus a1 minus a1 bar. Okay. So now I have a differential equation, although I don't know yet what a1 is, right? Those are yet to be determined. Okay. So I need to go to next order. And what's going to happen is I'm going to get another equation that's going to help me determine what A1 is. And that's actually going to be coupled back to B. Okay. So we have to go all the way up to order epsilon squared in this case in order to figure out what our amplitude is so that we can create this condition on A2. Okay. So at order epsilon squared, again, I have my same old operator on the left-hand side acting on y4 now. And I have a much bigger mess of terms on my right-hand side. I a1 prime sigma e to the I t over 2. That means A1 is going to show up in my amplitude equation. I have A2 also showing up, so that might be worrying because you say, well, how are we going to get rid of those? Because I'm not going to know what A2 is. Okay. I have a minus A2 e to the 3it over 2 minus A0 over 2 e to the 3it over 2 minus A0 over 2 e to the 5it over 2 minus A0 over 2 e to the it over 2 minus, and there it is, little a2 a0 e to the it over 2 plus complex conjugate of all that stuff. So to eliminate secular terms, I know we have like 30 seconds left. Okay. I need that I a1 prime of sigma is equal to a2 plus a2 bar plus ib over 2 plus a2ib. Okay. And similarly, I a1 bar prime is equal to a2 plus a2 bar minus ib2 minus a2ib. Okay. So if I just take these and I sum them to or subtract one from the other, I finally get minus a1 plus a1 bar prime is equal to ib plus 2a2ib. Okay. And it's 10 o'clock now, but I'll have to finish it, but I'll just tell you that this now gives me a differential equation for this sum term here. And if we look back at this equation, that's all I need. I just need a differential equation for the sum of these terms here. Okay. A2 is gone from this equation. So this couples me back to B, and I have a second order equation, which is going to have exponential solutions. I look in that exponent and I create a condition that makes sure that I just have an imaginary coefficient of my what appears in the exponential, and that will give me a condition that'll create stability for me. Okay, so I'll finish this up at the beginning of lecture next time. Well, actually, that's going to be recorded and put on the web. And we'll do kind of a practice problem of this on Friday. So we'll, you know, break up it into 2 or 3 groups and just do practice problems and sort of Q&A around this. Okay. So look for an email. I'll send you an email when I post the next lecture. It'll be finishing this up, and then also going through, I think, linear waves essentially, and maybe some nonlinear waves. And then yeah, I'll see you on Friday for kind of a practice problem session. Okay, that's it. Let me know if you have any questions. Otherwise, see you on Friday.
Thanks, Zach.
Thanks.